Hi, welcome to Hubble's Universe Unfiltered. I'm Dr. Frank Summers of the Space Telescope Science Institute. Now, we've given this episode a little bit of a provocative title, but I want to say right up front that there's nothing wrong with the Hubble Space Telescope. Matter of fact, what we're going to show you is just how well it's really working. Now, the coma in the title of the episode doesn't refer to being comatose. It actually refers to the constellation Coma Berenices. Now, Coma Berenices isn't the most spectacular of constellations. It's really just three bright stars. And when I first looked at this image, I said, oh, well, here's 1, 2, 3 bright stars. Unfortunately, they're not in Coma Berenices. This is actually Vindi Matrix in Virgo. This is Cor Coriolis in Canis Venatici. And this one is De Nebula in Leo. So the 3 bright stars in this image aren't actually in the constellation Coma Berenices. So where is Coma Berenices? It's actually got these 3 bright stars, Alpha, Beta, and Gamma Berenices. If you can't see those, let me put some arrows next to them to try and show you where it is. So they really are only what we call 4th magnitude stars, where 1st magnitude is the brightest, and then 2nd magnitude is a little dimmer, and 3rd magnitude. And the brightest stars in Coma are really only 4th magnitude stars. The only thing really visually interesting about the constellation is this cluster of stars. This cluster of stars is called Melat 111, and it's special because it's a relatively nearby cluster of stars. It contains, about 40 stars, and there are only 2 other clusters of stars that are closer, so this is a very good cluster of stars to study. Now, although it's a relatively boring constellation, it does actually have an interesting story behind it. And the story goes back to this guy, Ptolemy. Now, Ptolemy was a Macedonian king of ancient Egypt. And I have to say, he's not the Ptolemy who was an astronomer. The Ptolemy who was an astronomer came about 400 years after this guy. This one is Ptolemy III, and he's famous for waging war against the Syrians. And he had a wife, and here is a bust of his wife, Berenice. And Berenice was famed for having beautiful, gorgeous long hair. However, she was very afraid that her husband was going to get killed in this war. So she pledged to the goddess Aphrodite that she would cut off her long hair if her husband returned home safely. Well, he did come home safely from the war, and she did as she pledged. She cut off her hair and put it in the temple of Aphrodite. However, during the festivities celebrating the victory, the hair disappeared from the temple. And this was a huge outrage. And the temple priests were going to be sacrificed. And now here comes the cool part. For one of the few times in history, it's an astronomer to the rescue. Conon of Samos, the astronomer, stepped in and said, wait, Aphrodite accepted your gift, and she loved it so much, she put it up into the sky as the constellation Coma Berenices. So, as you can see, Berenices is here depicted with short hair, not the very long hair she was famous for, because her hair is supposed to be up in the sky. Now, this is the stick figure of the constellation, and I gotta tell you, it doesn't say much in terms of hair to me, but if you have some kind of imagination, you can actually draw it in. And this is how Johannes Hevelius depicted it in 1690. And so these are the 3 stars of Coma Berenices, Alpha, Beta, and Gamma. And right next to Gamma is that clusters of stars, which I guess sort of represents the hair flowing back this way. This bright star up here would be Cor Coriolis, as we saw in the previous image. And the other 2 bright stars would be down here, and it doesn't look like Hevelius has depicted them. So it's kind of a neat story behind the constellation because, it's named after a person in historical story, and an astronomer gets to play a significant part. But astronomers are much more interested in a different thing about Coma. It's this region right up here in the top of Coma. And when you look in very close, you see this. Now, this is, to an astronomer, obviously a star. You see the big spikes here. And this is another star. So these are 2 stars in our Milky Way galaxy. Everything else here, all of these fuzzy blobs, are other galaxies. So all of these fuzzy blobs, this is a giant cluster of galaxies. Just like we saw stars can cluster, galaxies can also cluster. So if a large galaxy like our Milky Way has about 100 billion stars, and you've got about 1,000 galaxies here, Really what you're looking at is about a quadrillion stars. And that's million, billion, trillion, quadrillion. That's a lot of stuff here. Now for astronomers, there are two important things about the Coma cluster. One is, first of all, it's a rich cluster, but it's a relatively nearby cluster, and that makes it easier to study. But it's not like the Virgo cluster. The Virgo cluster is actually a little bit closer than Coma, but it's so close that it's spread out across a wide swath of the sky. And it's kind of hard to study because you have to look in so many different places. With Coma, you can see that you can relatively get an awful lot of galaxies in one image. The other reason that makes Coma an interesting galaxy cluster to study is that it's near the galactic North Pole. Now, our Milky Way galaxy is a spiral galaxy, and it's relatively pancake-shaped. Okay? And if you're looking out through the pancake, there's a lot of gas and dust that's blocking your view. But if instead you look perpendicular to the pancake, to the north or south, to the poles, you can then look through much less gas and dust when you want to study things that are outside our galaxy. For instance, other galaxies. So having a cluster of galaxies that's located near the galactic North Pole makes it a really well-studied cluster, and so we've studied Coma in amazing detail. Now, I said it's a relatively compact cluster. That's really for ground-based observations. Hubble's high-resolution observations actually don't cover a large enough area to get Coma into one field. So Hubble has to study different small parts of Coma. And we're looking at an image that studied this part of the Coma cluster. And here is Hubble's image from that, and you can see the galaxies in much more detail. But actually, this is a high-definition monitor, but it still doesn't contain all that Hubble shows. Because while this has about a megapixel of detail, the true Hubble image is 83 million pixels, 83 megapixels. Compare that to your digital camera, which most of us have cameras that are a few megapixels. Well, this full image would be 83 megapixels. So I'm really not even showing you all the detail there is there. But let's take a look at some of the galaxies in Coma, and what I'll show them to you is we're going to show them to you pixel for pixel. So let's take a look at these 4 galaxies, and these small cutout regions will contain every pixel that Hubble looks at. Now, this first galaxy is a spiral galaxy, sort of like our Milky Way. You can see sort of the pinwheel structure around, and again, it would be a pancake-shaped galaxy, a flat galaxy. This one, somewhat tilted to our line of sight so that you can see some of the spiral structure. The second galaxy is also a spiral, but instead of being tilted to our line of sight, it's pretty much edge onto our line of sight. So here you can see the spiral galaxy's disk structure, but of course you can't see any pinwheel shape. You have to do other analysis to be able to see, oh, is it really a spiral galaxy, so that you can see the spiral structure. What you see especially here is that if the stars are going to be confined to this thin little disk, then they're all basically orbiting within a plane. All right, they're very well-ordered galaxies because the stars are basically all orbiting within a plane. Not so with our third galaxy. Our third galaxy is a different class called an elliptical. Now, if you take a circle and you stretch it, it becomes an ellipse, and hence the name elliptical. So it's a great big ball of stars. And in order to get this shape, the stars wouldn't all be in a nice orderly pattern. They'd actually be going off in every different direction. So if you take all the orbits of stars and you randomize them and mix them up and let them go every different direction, you get an elliptical galaxy. Our fourth galaxy to look at is sort of a combination of the previous two. It's called a lenticular galaxy, or in astronomical terminology, they call it S0, as in sort of the spiral category 0. And what it consists of is you can sort of see a disk here. It has a disk like the spiral galaxies, but it also has the big ball of stars of the elliptical galaxies. So it's sort of a combination of the elliptical ball of stars with the spiral disk. What's interesting about these different shapes is, well, when you look at the full Coma cluster, you see many more ellipticals and lenticulars than you would expect. If you take a galaxy and you let it form in isolation, not really near other galaxies, you tend to get spiral galaxies. Spiral galaxies seem to be what nature prefers when you form a galaxy in isolation. But when you look inside clusters, you find many more ellipticals and lenticulars. We call this the morphology-density relationship. The morphology of galaxies changes with the density of the environment in which you're looking, so that you get an awful lot more of these big ellipticals. Matter of fact, these are giant cluster ellipticals, a typical thing to find at the center of a cluster of galaxies. The question would then be, well, what would cause this morphology-density relationship? The simple answer is interactions between galaxies. When you take two galaxies and you pass them by one another, they can distort each other's morphology. And they have a tendency to randomize the stellar orbits. Remember all those, in a spiral galaxy, you've got nice circular orbits all on a plane? Well, if you disturb it, those orbits tend to go all over the place. And what do you end up with? You end up with more elliptical galaxies. And Coma is one of the densest clusters of galaxies that we know of. So the morphology-density relationship is at one of its strongest points here in Coma, and it's a great place to study these ellipticals and lenticular galaxies. Now, there's one more interesting thing about the Hubble image, and it's not the various galaxies you see here and here, but it's actually in the center here where you're not looking at any of the galaxies in Coma. Instead, what you're looking at is all these background galaxies that are well beyond Coma. The Coma cluster is about 300 million light years away. That means the light from Coma takes 300 million years to cross space before we see it. These galaxies are probably 1 billion, 2 billion, 3 billion, several billion light years away, much further beyond Coma. And you can see, there are the standard spiral shapes and ellipticals. But if you go way far out, you actually get some really strange shapes for the most distant galaxies. And, well, I'd like to discuss those, but that's really another story for another episode of Hubble's Universe Unfiltered. The point is that we see these galaxies all over the place when we have these deep Hubble images, and they're really quite an amazing number of galaxies out in the universe for us to study, both near and in the very distant. So, let's take a look at where we've been. We're going to start with that wide field image of Coma Berenices, and then we slowly zoom in to see the Coma cluster. This is the Digital Sky Survey image. You can see all of the 1,000 galaxies of Coma, but of course we don't stop there. We keep on digging further in. And now we bring up the Hubble image, and we don't stop at the beautiful, gorgeous Hubble galaxies, but we instead keep diving past those Hubble galaxies until we get to these very distant galaxies on the other side of the universe. So that's Hubble falling into Coma. Not going comatose, but falling into the Coma cluster of galaxies and exploring the wonderful galaxies out there. That's it for today's episode. We'll see you next time on Hubble's Universe Unfiltered.